Good morning. Welcome to the physics video lecture. It is Physics 105A video lecture 15. What are we talking about today? It's going to be damped oscillations. So we're back into the small oscillations world. Let me say a bit about complex numbers and complex exponentials to set the table here. So we had learned that, well, first of all, e to the theta cosine theta plus I times sine theta. This is due to Euler, and we showed this. So I theta. Boom. And also, if z equals e to the I omega t, then the second time derivative of z is minus omega squared times z itself. Well, that's just our equation of the harmonic oscillator. You have to make sure we realize one more thing, because after all, for the harmonic oscillator, we're actually looking for a real number, a number as a solution, and this is a complex number. But the real part of a complex number can just be extracted very easily. And as long as you're only operating with linear operations, then you can interchange the extraction of the real part and the operations that you're doing. So let's go ahead and make sure we're clear on this. So for linear operations, we have the real part of the linear operation here. Let's write linear operation L. For linear operations L, the real part of the linear operation applied to z is equal to the linear operation applied to the real part of z. Okay, so we can just interchange the two. Now, what are these linear operations? First of all, addition. I'm going to ask you guys to do this. You can leave room in your notes to fill it in, but just put a couple, these are a couple one-liners on the homework. We have real part of z1 plus z2 is equal to the real part of z1 plus the real part of z2. Simply write z1 equals x1 plus I y1, z2 x2 plus I y2, and then do the operation. This is trivial but important. And then multiplication by a real number. So if alpha is real, part of the real numbers, then the real part of alpha z is equal to alpha times the real part of z. Now, very important to note that this basic thing is not true for multiplication and for nonlinear operations in general. So 3, important note, real part of z squared is not equal to the real part of z, the quantity squared, okay? Not equal to, very important, and you guys want to show this as well. Okay, so all three of these are homework. And so good. So this is homework here. Just do them to make sure that you're clear on that. Kind of another interesting and fun thing is to, I'll just add this as another note. And we'll put this as homework as well. Because we have this Euler relation up here, we can we have e to the I a plus b is equal to e to the IA times e to the IB. Okay? So you can use this. I'll do on the left side here cosine a plus b plus I sine of a plus b equals question mark. Okay. Here's the thing. I just filled in the left side here. If you guys do the right side according to Euler's formula and multiply it out, you will get the two the cosine and sine sum formulas. Okay, they're just built right into here. So homework is to prove those formulas. Okay. In other words, e to the IA cosine A plus I sine A time, in parentheses, times e to the IB, right? And see what comes out. Okay. Those are just the addition formulas for the sine and the cosine. Let me write here. And you don't have to memorize them anymore, although you probably have, but you can always rederive them using this formula. So yeah, there's plenty of interesting stuff that can be done here. What we're going to do next is talk about the damped oscillator, and we're going to use this fact because it's going to make our solutions easy, and at the end of the discussion is when we can take the real part. Okay, so that's what this was just setting up. Okay, so now we're talking about oscillations, and I'll return to our Newton's law way of looking at things just to remind us of this. So now we're talking about oscillations, and we're kind of going to generalize. We were looking at functions of this form, right? Forces that are just functions of x. But for our harmonic oscillations, minus k times x. Okay? And we've worked that. Now what we're going to do is take a system like this and add friction. So suppose there is friction. Well, friction is something we would add to the right side of this equation. So I can say we have minus kx plus a frictional force, and we're going to have a velocity-dependent frictional force. So plus some function of x dot. So let's go ahead and write that here, velocity dependent. Okay, velocity dependent. And you'll remember we talked about this earlier on, and what we argued was that for sufficiently small velocities, we're just going to replace this function of x dot with a constant. So minus kx plus something times x dot. And we had even given an example, Stokes' law for motion through a fluid. Okay. So I'll just put that here as well. Recall f of x dot is just equal to minus bx dot for small velocities. Example. F equals, I'll just put magnitude of F equals 6 pi eta r v, right, for a small sphere moving through a through a fluid with viscosity. So we could have a pendulum which has some finite size and it's moving through the air, and the air is a fluid with viscosity. Okay. So there's an example, and that means our new differential equation equals minus kx minus b times x dot. So this is going to be the damped oscillation. So there is now friction. And we're going to make a couple of substitutions for convenience. Okay. Oh yeah, this is a constant. If you're moving through air and you're a sphere, then there's actually a law for that. Okay. And also remember, this law itself, when we extracted it out of a more general situation, this law itself is true for small amplitudes, right? Small velocities. So physically, we're covered here. Okay, now we're going to define omega 0 is going to be the square root of k divided by m, and 2 times gamma, you'll see in a minute, the 2 is just for convenience. 2 times gamma is equal to b divided by m. And if we do that and bring everything to the left side, and we're basically dividing this equation by m, bringing everything to the left side, and we end up with, we obtain 2 derivatives in x plus 2 gamma times the first derivative plus omega naught squared times x equals 0. So this is our differential equation of the oscillations with friction. And that's a friction that opposes the direction of motion, right? That is acting opposite the direction of motion. So we have the minus x dot there. Okay, so how do we solve that? Well, it turns out this is a linear differential equation with constant coefficients, and we can do the complex trial solution for it. Okay. So what we'll do is, I could just call it x, but let z equal a e to the pi omega t be our trial solution, and we can take the real part of this when we're done. That's the whole point of the discussion up above there. Be our trial solution. See, this is the general solution. The complex exponential is the general solution to a whole class of linear differential equations with constant coefficients. I'm going to write that down. So you could have a whole string of higher derivatives even, and it would still be generally this way. You could have a matrix linear differential equation. Maybe we'll set that up later. Then it would also have this general form as a solution. Okay. So yeah, let's just put this down as our terminology. Linear differential equation with constant coefficients. So that you guys, you can always look this up if you want to get in there deeper knowledge. Okay, constant coefficients. Good. So here's our trial solution, and all we do is apply these operations to this trial solution here. Let's see what happens. Okay. Well, we'll do this directly underneath. 2 time derivatives Okay, 2 time derivatives. That's just going to bring down I omega and I omega again. So we're going to get I omega quantity squared A e to the I omega t. Okay. So the next operation is this one here, plus 2 gamma. Now we're going to take one derivative, one time derivative. This brings I omega down once. I omega A e to the I omega t. And then omega naught squared, that's a simple multiplication. And A e to the I omega t equals 0. So look, we have common factor A and e to the I omega t. E to the I omega t is never equal to 0. And therefore, we're left with a polynomial. I'll go ahead and factor that out. So A e to the I omega t. And then what are we going to have over here? We're going to have I omega, the quantity squared, so that's minus omega squared, plus 2 gamma I omega, plus omega naught squared. Got some extra room there, but this is the end. So this is equal to 0, and so we have a solution to this differential equation when the expression in parentheses vanishes. And that means there are values for omega that we have to solve for, right? Omega was not known, we just plugged it in up there as the trial solution. Okay. So we're going to solve, so next, solve for omega. Right here. Okay. So we set this expression in parentheses equal to 0. Okay, it looks like we're going to need the quadratic formula. Let's see here. Factor out a -1, so we will have omega squared minus I times 2 gamma omega. Well, actually, I don't have to factor that out. Let's just write this out. Minus 2 gamma I omega minus omega naught squared is equal to 0. So good, we'll solve omega using the quadratic equation, solve for omega using the quadratic equation. So omega is equal to 1/2 negative b, so 2 gamma I plus minus the square root of this b squared minus 4 gamma squared minus 4 times 1 times omega naught squared. Minus 4 omega naught squared. Close parentheses. Okay. Now we're looking at clearly a square root of a negative number here. So let's see what happens. First of all, and you can also see why it was such a good idea to put that factor of 2 in there, because then we're going to be able to pull that out. So omega equals I gamma plus minus oh, I use the I omega t, so what do we have here? Minus 4ac, this should have been plus. Okay. And this should have also been plus. Okay, let's go with field. Squared minus negative b gamma I squared. Oh, we have minus right here. Minus 4i AC plus. So the negative b, of course, the minus sign squares is positive, but the I squares minus. Good. So now we divide by the 2, gamma I. We have 4 omega naught squared divided by, putting the 2 in there, 4. So that gets rid of both of these 4s, and we have, I'm going to write omega naught squared minus gamma squared. So there we go. It's equally possible, and that's actually what I was thinking of for a moment. It's equally possible to just set this up with a e to the, say, lambda t or something, okay? And then you solve a similar polynomial, which will end up with the same answer. But this is fine. Let's go ahead and use this one. Because the very I'll just say this right now, the very general solution is just an exponential, and whether it's real or complex actually comes out in the mix, okay? But this is fine, okay? So what we have found is an omega with an imaginary part and a real part, although if this gamma squared, which is the damping, right, the friction, if this is too great, we could end up with a minus sign inside of here. That'll be a special case. But what we're going to do is check this now for the first case. Gamma squared is less than omega naught squared. Okay. That's called the underdamped case. Underdamped. And we'll go ahead and do this right here. So we're going to go back into our solution. So now z is equal to a e to the I omega t, so I times this thing here, I gamma plus minus root omega naught squared minus gamma squared t. So here we have an interesting property. E to the I times the I is minus, right? So we're going to get a e to the minus gamma t right there, and we'll use the multiplicative property of the exponential. The rest is going to be e to the plus minus I root omega naught squared minus gamma squared times t. Okay. And what about the real part of this? Let's go ahead and take the real part right away. Here's our answer. So we have A actually could have been a complex number to begin with, and we'll deal with that later. E to the minus gamma t is real. And this e to the I omega naught squared minus gamma squared t, that is our oscillatory part. So I'm going to take out the real part right now. So x equals the real part of z is going to be a e to the minus gamma t. And we'll just take the cosine root omega naught squared minus gamma squared t. That's good enough. After a while, you'll get used to just having this expression and seeing that it's this cosine. Okay, once you work with these often enough, you're usually just satisfied to have this thing, to be looking at this thing right here. But there we are. We have a e to the minus gamma t cos omega naught squared minus gamma squared times t. So let's look at the physical. We have to look at the clock before we do that. Good. Yeah, let's graph this thing. So we're going to graph this right underneath. We've got t, we've got x of t, damped oscillations. We'll go ahead and title this damped oscillations. And we can draw an envelope first. Now this is e to the minus gamma t is here's minus a. We're looking at something that decreases more or less rapidly. We can draw the envelope like that, and then we see that we have oscillation. This is no longer a strictly periodic system, because it does not return to its original position. It is oscillating. The frequency, you'll notice, is slightly lower than it would have been without the damping. Damping slows down the oscillation a little bit. In the limit as gamma goes to 0, well, this turns flat here. Right? Gamma goes to 0, just turns into a 1, and we're back to cosine omega t, omega naught t. And you could ask, what about the phase that we had in the past, right? We had an omega naught t plus alpha or something. Well, so these are underdamped oscillations. Underdamped oscillations. I'll get to that where that phase is hidden in a moment. But this is the first case. So let's go ahead and just mention the second case. That would be where gamma squared is greater than omega naught squared. Gamma squared greater than omega naught squared. In that case, we've got a purely negative number under the radical. We pull out I, okay, and we end up with what's called the overdamped case. Where's our function? Yeah, when we plug that in here, we get e to the minus gamma t, and then e to the plus minus something else times t. But it's no longer oscillatory. You guys may want to check that out. Overdamped. Z equals a e to the I, and then we just plug in I gamma plus minus I times root gamma squared minus omega naught squared. Okay, so we pulled out the I, pulled out the minus squared minus 1 gamma, and then we would have a t right here. Okay. Now, I times I is going to be -1. Here, I times negative I is going to be +1, but this is always going to be of less magnitude than the gamma itself, because there's something being subtracted from it. So the behavior of this thing is purely damped. It starts out somewhere and it just decays to nothing. So that's the overdamped case. We don't really have much to do with it, but it's one of the solutions. The third case is interesting. It's called the critically damped case. So the third case, omega naught squared is equal to gamma squared. Then there is more than just this solution that we have right here. I'm going to assign this as homework because it's an interesting basic little calculation. Critically damped. Critically damped case. And we'll put this as a homework problem. Homework. Let, like I said, omega naught equal gamma. They're both positive. Okay, so squared or not is no problem. This time we're not using the complex formulation. Let x of t equal some function of t e to the minus gamma times t as your trial solution. And take this as trial solution for our differential equation. Namely for x double dot plus 2 gamma x dot plus omega naught squared x equals 0. So this is a real one this time, okay? Real. And what you'll do, what will happen when you go ahead and go into the differential equation with this trial solution, you'll get a differential equation for f of t, which is, by the way, a very simple one. Okay. Find f of t. And then f of t times this, and you get a critically damped. And the critically damped one has more of a resemblance to this than it does to that. Okay, it's also not oscillating at all. It's called the aperiodic solution. So when you combine this f of t that you get out of this differential equation with e to the minus gamma t, you get the aperiodic solution. So x of t is this f of t e to the minus gamma t. It's called the aperiodic solution. Okay, so one more consultation with the clock. You know, I can just do one more thing here and then we'll have rounded out this discussion for today. Remember I said, what happened to the cosine, omega t plus alpha? Because I said when we let gamma go to 0, we're going to get back our original solution, but we are missing that phase. So I'm going to wrap things up by talking about that. It's actually hiding in here. Because I did not have to make this be a real number. Okay. In my solution here, I assume that a is real, right? But what if a is a complex number? Then I'll do this on the left side. important note. Z equals A e to the I omega t, which is what we took into this differential equation up here. So we can also have, we can write Z equals the magnitude of A times e to the I alpha, okay, times e to the I omega t. Okay. So if A is a complex number, just a constant complex number, then it has a magnitude and a phase. Remember? That would be alpha, that would be A, that would be the point. That would be the complex, this complex A right here. And then this e to the I alpha can of course be absorbed in the I omega t plus alpha. And then we solve for omega, we get this, and we've got the alpha as well. So we'll run into this again. And yeah, that'll bring the, like I said, that'll bring the alpha into here, equals A e to the I omega t, omega t plus alpha. And notice the alpha was not being multiplied by the t, okay? So it would just be here, cosine this times t plus an alpha. So I'll finish that off by writing x equals real part of z, a magnitude, and then e to the minus gamma t cosine root omega naught squared minus gamma squared t plus some alpha. Okay, good. That's plenty for now. Gonna round this out. Okay, good. We'll leave it at that. See you guys next time.